Welcome to Lecture 5.2, Boundary Conditions for the Heat Equation. Let's begin with a quick review of what we learned at the end of the previous lecture when we solved example 1a, which was the following boundary and initial value problem for the heat equation. That's the PDE, UT equals C squared UXX. That describes the temperature of a bar of length L, although in this lecture we're going to assume that L equals 1. It just makes the math easier. We have two spatial derivatives here, so we need two boundary conditions, and these things describe the temperature at the boundary being fixed for all time t at 0 degrees. So we can imagine that this bar is insulated along the interior, so heat can only move laterally, but it is uninsulated at the endpoints, and the bar is sitting in a room with ambient temperature 0 degrees. Finally, we have one time derivative, so we need one initial condition, and that is this parabola. And it is not hard to imagine what happens as time goes on with this heat. That's going to escape through the boundary, and so this curve is going to flatten out. And then as time goes to infinity, it approaches a steady state of 0 degrees. Remember how we solved this. We assumed that there was a solution of the form f of x times g of t. And then we plug this back into the PDE. We separated variables. We put all the functions of x on one side and the functions of t on the other side. And we argued that because those were independent of time and position, that had to be a constant. And that gave us two ODEs. One of them in f and the other one in g. And the one for f involved two boundary conditions. And we got a boundary value problem. So that gave us a solution for each eigenvalue n. We got a solution of the form fn times gn. And by linearity, or superposition, if we had a collection of solutions, then any linear combination of them is a solution as well. So that's what got us the general solution, which is the infinite sum of bn times sine of n pi x times e to the negative c n pi quantity squared t. In general, these were n pi over L, but we're just letting L be equal to 1 here. Finally, we had to use the initial condition. So we plugged in 0 and set this, well, when we plugged in 0, the exponential goes away, and now we have an infinite sum of sines that we had to set equal to this polynomial x times 1 minus x. To do that, we have to write this in a Fourier sine series, and then we equate coefficients. And that's how we got that the Bn is equal to 1 minus negative 1 to the n over n cubed pi cubed. And now I'm going to slightly tweak this example. I'm going to set the boundary to be fixed at 32 degrees instead of 0. And I have to shift up the initial condition as well. So here's a picture of what this looks like. So we have the same bar, but now the endpoints are 32 degrees. The bar is still insulated along the interior and open at the endpoints. And the initial condition is the same parabola except shifted up by 32. So it's not hard to use your intuition to see what happens as time goes on, that this is going to flatten out, and eventually, over time, the bar is going to approach a steady state of 32 degrees. So how does this function of x and t compare to this one up here? Well, obviously, it's just shifted up by 32. In other words, the solution to this is just u of xt equals the solution to the example 1a. So that's the infinite sum of 4 times 1 minus negative 1 to the n over n cubed pi cubed sine of n pi x e to the minus c n pi quantity squared t plus 32. So let me box this. And these boundary conditions, because they are non-zero, they are often called inhomogeneous boundary conditions. So I'm going to write that down. And it's not surprising that if you look at this solution, that this plus 32, this is the steady state solution. because it is the limit as t goes to infinity of u of x and t. And I'm going to call this first part the homogeneous solution, u h of xt. So this is the solution to the related boundary value problem, initial value problem, where the boundary conditions are homogeneous up here. And this is how we are always going to solve PDEs with inhomogeneous boundary conditions. Find the steady state, make them 0, solve it, add those together. It's just like what we did with ODEs. Now I'm going to show you how this arises mathematically just with a simple change of variables. This is what we did with ODEs. I told you that any time that you are making an equation homogeneous, you're secretly doing a change of variables. And the example that I used was Newton's second law, or I guess Newton's law of cooling. There's only one of those. So T prime equals negative K times T minus 72. To solve this, well, you can look at it and say that the solution is, well, there's a particular solution, which is Tp equals 72, and the homogeneous solution is C e to the minus kt. You can just do that in your head, but what you're really doing is you're doing a change of variables. Let's let y be t minus 72, so let's subtract off the steady state solution. And then if you plug this back in, you get that y prime equals negative ky, and the solution to that is the homogeneous solution. So it's the same thing here. We are going to let v of x and t be the solution to the inhomogeneous equation. Now I should say that the PDE is still homogeneous. There's no other terms here besides u's with derivatives, but the boundary conditions are not. So we're going to subtract off the steady state solution. That's 32. So v is u minus 32. If we do this, then vt is clearly equal to ut, because we're just adding on a constant that goes away with differentiation. And similarly, vxx is equal to uxx. Now let's compute the boundary conditions of v. So v of 0 and t is u of 0 and t minus 32, which is 32 minus 32, and that's equal to 0. Similarly, the right boundary condition, v at 1 and t, is equal to u at 1 and t minus 32, which is equal to 0. We also have an initial condition. So v at time equals 0 is just u of x and 0 minus 32, the steady state solution, and so that leaves us with just x times 1 minus x. So in summary, what we have is, when we change variables, we get that vt equals c squared vxx, subject to the boundary conditions v of 0t equals v of 1t equals 0, and the initial condition v of x 0 equals x times 1 minus x. So notice this is exactly what the equation of the homogeneous boundary value problem was. So in other words, we have a solution v of x t. So we know the solution to v, it's the same thing as what we have up here for u. So that's the infinite sum of 4 times 1 minus negative 1 to the n over n cubed pi cubed, sine of n pi x, e to the minus c n pi quantity squared t. And so we conclude right away that, well, that u, which is what we're trying to find all along, is just v plus 32. I'm not going to rewrite that whole thing, but u of x t equals v of x t plus 32. And let me just mention why it's not going to work to do what you might be tempted. It's just to solve this directly using separation of variables, because that does work for ODEs, but that's not going to work for a PDE. And the reason is because think back to how we used these zero or homogeneous boundary conditions. Remember that? So this first one, we wrote as f of 0, g of t equals 0. And we were able to conclude that this was a number multiplied by a function of time that was non-zero, and we got 0, so we said that f of 0 had to be equal to 0. However, down here, if we were to try that, we would get that f of 0 g of t would equal 32. So g of t is going to be some function of time, not a constant, and there's no way we can multiply such a function of t times a number to get the constant function 32. That's not possible. So what that tells us is that there is no solution of this equation of the form a function of x times a function of t, like there is here. I mean, here we have a whole bunch of them. For each n, we have one like this. We don't have that down here because we can't get this 32 out of there. That's always going to stick around. So the moral is, solve the homogeneous equation first, find the steady state solution, which you can do by inspection, and add them together, and that's your final solution. Now, I'm going to slightly tweak the previous example, and I'm going to call it 1c. The only difference is that I'm going to set the right endpoint to be 42, and I'm going to adjust the initial condition accordingly. So in example 1a, we had this bar of length 1, and there was insulation along the interior, but not at the endpoints, and the endpoints were fixed at 0 degrees, and the initial condition was this parabola. And as time went on, this parabola became flatter and heat became flatter and flatter, and in the end it approached a steady state of 0 degrees. Now in this example, we have the same bar. It's insulated along the interior as before, except now the left endpoint is fixed at 32 degrees and the right endpoint at 42 degrees. So maybe it's uninsulated at the endpoints and the left endpoint is outdoors where it's 32, and the right endpoint is indoors in the fridge where it's 42. And finally, the initial condition is this parabola shifted up by 32 minus 10x, so that's going to look something like this. Notice that 32 plus 10x is just a straight line, like this. And using your intuition once again, as time goes on, the temperature of this bar is going to become more uniform and flatten out until, in the limit, it's going to become this straight line solution. It's going to increase linearly from 32 at the left endpoint to 42 at the right endpoint. So this is the steady state solution, 32 plus 10x. Now this is the first time that we have seen a non-constant steady state solution. And that makes sense if you think about what the steady state solution means. It's the limit as t goes to infinity of u of x and t. So when we've had regular ODEs in one variable, time, and we took this limit, if there was a steady state solution, it was constant. But now we have a second variable. So it can certainly happen, and it is, in this case, the case, when you take the limit of that and the variable t goes away, but now you have something that's non-constant in x. The solution to this, not surprisingly, is, so this series of red curves is basically what we have up here, shifted by the steady state solution. So I'm going to write that as uxt equals the steady state solution plus the homogeneous solution. Again, the solution to the homogeneous boundary value problem. And that's 32 plus 10x plus the infinite sum of 4 times 1 minus negative 1 to the n over n cubed pi cubed sine of n pi x e to the minus c n pi quantity squared t. So let me box that. So as before, we use the same method. We solve the homogeneous part first, find a steady state solution, and add them together. I want to finish this slide by just showing you how this follows from a change of variables, like we did in the previous slide. So now I'm going to let v, as before, just be the solution and subtract off the steady state solution, which is 32 plus 10x. So minus 32 minus 10x. Now Vt equals ut, because adding these terms that don't involve t doesn't change the time derivative. And Vxx equals uxx, because even though this has an x, there's only one power of x and there's no x squared. Let's check the boundary conditions. So v of 0 and t equals u of 0 and t minus, what is it? So minus the steady state solution, which is 32 minus 10 times 0, which is 32 minus 32 minus 0. So that's 0. And then v at x equals 1 and t equals u at x equals 1 and t minus 32 minus 10 times 1. So that's minus 32 minus 10 times 1, and that's 42 minus 32 minus 10, which is 0. So this always happens. Finally, the initial condition right here is just v of x0 equals u of x0, which is clearly just x times 1 minus x, and we subtract off that part. So it's x times 1 minus x. So in other words, in v, once we do this change of variables by subtracting off the steady state, what we get is exactly the homogeneous boundary value problem. So as before, u of xt is going to be v of xt plus 32 plus 10x. So this is mathematically why it holds, or if you trust your intuition, you can just look at the picture and understand why it holds from that. We're seeing a familiar theme, that is to solve the initial and boundary value problem for the heat equation, where the left endpoint is fixed at A degrees and the right endpoint at x equals L is fixed at B, and an initial temperature of h of x. First, solve the related homogeneous problem. Set these things equal to 0 and subtract off the steady state solution from h and solve that. And add that to the steady state solution, which is going to be a line, a plus b minus a over L times x. And it's clearly going to be a line because if you just do some algebra, you draw the straight line that goes through 0a and LB. That's clearly going to be of the form of slope b minus a over L times x plus y-intercept a. And that's the steady state solution. Next, we come to example 2, which is a similar boundary and initial value problem for the heat equation. The only difference is now, instead of fixing the temperature to be 0 degrees at the endpoints, we're fixing the rate of change to be 0 degrees at the endpoints. So here's a picture of this. Now this is the rate of change with respect to position, which means that heat cannot flow through the endpoints laterally. And this describes a situation when the endpoints are insulated. Now the interior of the bar is already insulated, so this means that the entire bar is insulated, so heat cannot enter or escape. If the initial condition is this parabola right here, then it's not hard to see, using purely intuition, that as time goes on, the heat will dissipate and flatten out, and it will approach a steady state solution, which is a constant temperature, and this is going to be equal to the average temperature of the bar, because heat is preserved, or conserved, I should say. And I'm going to call this A naught over 2, and that should not surprise you. More on this later. So let's write that down. Our intuition is that the limit as t goes to infinity of u of x and t, this is the steady state solution, and that this is going to be the average temperature. Now let's solve it. So I'm going to assume that there is a solution of the form f of x times g of t. And let's take some derivatives. So u t is going to be f of x g prime of t, and u xx is going to be f double prime of x g of t. And let's compute these boundary conditions while we're at it. So u x of 0 t is f prime of 0 g of t, and if that's equal to 0, now we have a number, f prime of 0, times a non-zero, non-constant function, g of t, equaling 0. The only way that can happen is if that number, f prime of 0, equals 0. Similarly, we have x, or ux at 1t is f prime of 1 g of t. So this is also a number times a function equaling 0. And that can only happen if the number f prime of 1 equals 0. So when we plug these equations back into the PDE now, let's write that down. So I'm going to plug back in. We get ut, which is f times g prime, equals c squared uxx f double prime g. And remember what we always do. We always divide by c squared fg, so c squared fg on both sides. And on the left-hand side, the f's cancel, and on the right-hand side, the c squareds and the g's cancel. So the left-hand side depends only on time. In other words, it's independent of position. And that's equal to something on the right-hand side, which only depends on position. In other words, it's independent of time. So if this is independent of position and time, then we can conclude that g prime over c squared g equals f double prime over f. It has to be constant. We'll call it a negative lambda. This gives us two ODEs. One for f is f double prime equals negative lambda f. And we have two boundary conditions up here that we're going to use. Let me box those so we can see them. So we get f of 0, or f prime of 0 equals f prime of 1 equals 0. And then we get an ODE for g. So g prime equals c squared g times negative lambda. So g prime equals negative c squared lambda times g. So we know how to solve this first equation. This is just a Sturm-Liouville equation, or just a boundary value problem. We did this exact one in lecture 4.1 on boundary value problems, although I guess it was with L instead of 1. So we got that lambda was equal to n pi, in general, n pi over L squared. So L is 1. So n pi squared. I'm going to call that lambda n. These were the eigenvalues, and the eigenfunctions were fn of x equals cosine of n pi x. And we got this for n equals 0, 1, 2, etc. Because when n equals 0, we got a constant function that was non-zero. Now we can update g, so g prime equals negative c n pi quantity squared times g, and this is just exponential decay. So gn of t equals e to the negative cn pi quantity squared t. So now we have a solution for each n. So for each n, that's a non-negative integer, we have a solution which is f times g, which is cosine of n pi x times e to the minus cn pi quantity squared times t. So by superposition, let me write that down, our final solution, or at least I should say our general solution, because our general solution satisfying the boundary condition, because I have not yet used the initial condition. The general solution is u of x t is the infinite sum from n equals 0 to infinity. I'm going to pull out the n equals 0 term, which is a constant, and just call that a naught over 2, because why not? So plus the infinite sum of, let's call this an cosine of n pi x times e to the minus c n pi quantity squared times t. So this is our general solution. It describes all functions that satisfy the heat equation with these boundary conditions before we impose what the initial condition is. Here is that general solution typed up. I ran out of room, so I'm using a new slide. Let me sketch once again what this situation looks like. So here's that bar. It's insulated at its endpoints and along the interior. Its unit length, and the initial condition looks like this, and then over time this is going to flatten out and approach the average value. Now all we have to do is use this initial condition. So let's plug this in and do that. So let's plug in t equals 0. If we do this, we get that u of x 0. Let's think about what happens. This exponential function just goes away, turns into 1, and we are left with a Fourier series involving cosines. So a naught over 2 plus n equals 1 to infinity of an cosine of n pi x, and we have to set that equal to this function x times 1 minus x. So this is x times 1 minus x. To do that, we have to write this function in terms of the Fourier cosine series. We don't have any choice with that. So recall what that means is we have this function that's defined from 0 to 1. And of course, being a parabola, it's not going to be periodic. It's going to be like this. But all we have to do is set this equal to a sum of cosines on this region. And we do that by taking the even extension and then extending that to be periodic. And that's what the Fourier cosine series is. Now, I'm not going to compute these integrals explicitly, every detail, because you can do that. I'll tell you what they are. So a naught is 2 over L, so 2 over 1 of the integral from 0 to 1 of x times 1 minus x dx. And it's easy to check that that's equal to 1/3. An is the integral of 2 over 1 from 0 to 1 of x times 1 minus x cosine of n pi x dx. This is a little trickier, but it's not hard to check that this is negative 2 times 1 plus negative 1 to the n over n squared pi squared. Okay, so given that, this function now equals a naught over 2, which is 1/3 over 2, or 1/6, plus the infinite sum of negative 2 times 1 plus negative 1 to the n over n squared pi squared times cosine of n pi x. So if we're going to set these two Fourier series equal, then the corresponding coefficients have to be equal. So a naught over 2 has to be equal to 1/6. We set those equal. And an has to be equal to negative 2 times 1 plus negative 1 to the n over n squared pi squared. So this has to be equal as well. So we're done. We have our particular solution that satisfies the initial condition, and basically it's this thing here except an is that. So let's write that down. So I call this the particular solution satisfying the initial conditions. I guess there's only one of them, and that's u of x t equals 1/6 plus the sum of this an times cosine of n pi x times e to the minus c n pi quantity squared times t. So that's our particular solution. Notice that as time goes on, each of these cosine waves is killed off by this exponential function, which acts as a damper, and what we are left with is this 1/6. So in other words, the mathematics matches our intuition that the limit as t goes to infinity of u of x t is equal to 1/6, and that, of course, is the average value, or the average temperature. Next, we have an example, the same heat equation, but we have mixed boundary conditions. The left endpoint is fixed at 0 degrees, and the right endpoint is insulated. So I'm calling this example 1.5. Here's a picture of that. Let's do as much as we can intuitively first without doing any math, as before. So the left endpoint, again, is 0 degrees. The right endpoint is insulated. The interior of the bar is insulated. And the initial condition is this sine wave. So that looks like this. Now heat can escape through the left endpoint. So intuitively, this bar is sitting in a room of 0 degrees. And as time goes on, this heat is going to flatten out. And in the long term, it will approach 0 degrees. And that's what should happen mathematically. Let's verify this. I'm not going to go through every single detail of separating variables. I just want to highlight the differences, and hopefully by now you've seen enough that you can follow along. So when we plug this back in, well, I'm going to at least say that we're going to let u of x t equal f of x g of t again. And we plug this back in, we are going to get f double prime over f equals, let's see, g prime over c squared g equals negative lambda. As before, nothing's going to change except these boundary conditions. Now we have this first one, u of 0 t is going to be f of 0 g of t being 0. That's going to tell us that f of 0 equals 0. And the next one is going to tell us the opposite, that u x of 1 t is going to be f prime of 1 g of t. And if that's 0, then f prime of 1 equals 0. So now we have the boundary value problem as before, f double prime equals negative lambda f, but our boundary conditions are different. We have f of 0 equals 0, and we have f prime of 1 equals 0. So these are mixed boundary conditions. And the equation for g is the same. So g, well, actually before we do that, let me just tell you what the answer of those to this boundary value problem is. We did this in the lecture on boundary value problems. So you may recall that lambda is now equal to n plus 1/2 times pi quantity squared. In general, it was that divided by L, but L is equal to 1. So I'm going to call that lambda n. And then sine, well, the eigenfunction, so I'm going to step ahead. The eigenfunction, fn of x, is sine of n plus 1/2 times pi times x. Okay, so now we can update function g. So g is going to be equal to negative c squared lambda g, which is negative n plus 1/2 squared pi squared, I forgot my c squared g. And the solution to that, that's just an exponential function. So gn of t is e to the negative cn plus 1/2 pi quantity squared t. So now we have for each n, so for each n equals, starting at 0, we could start at 1 if we wanted to make this an n minus 1/2, but it doesn't really matter. We have a solution un of xt, which is fn of x gn of t, which is sine of n plus 1/2 times pi times x times e to the minus c times n plus 1/2 pi quantity squared times t. So our final solution, I don't want to say our general solution, because again we have not used the initial condition yet. So our general solution is u of x t, this is the infinite sum from n equals 0 to infinity of, I'm going to call it a or b, how about bn, un of x t. So that's the infinite sum of n equals 0 to infinity of bn sine of n plus 1/2 pi x times e to the minus c n plus 1/2 pi quantity squared t. Okay, now what? What do we have left? We have the initial condition. Let's plug in 0 and see what happens. So let's plug in t equals 0. And if we do that, we get u of x 0. When we plug in 0, the exponential function goes away. N equals 0 to infinity of bn sine of n plus 1/2 pi x. We have to set that equal to the initial condition, which is sine of pi x over 2. So this is sine of pi x over 2. Now I intentionally did not make this a complicated thing where you'd have to compute a Fourier series because of these half integer things, but I claim this is, oh, I got to put a 5 in front, don't I? Yeah, because there's a 5 right there. So I claim this is actually even easier. We don't need to compute a Fourier series. Now what is this left-hand side reduced to? Notice this left-hand side, I'm going to do it up here, so this is b naught times the sine of 0 plus 1/2 pi x. So that's pi x over 2 plus b1. Yeah, isn't b naught kind of weird? Maybe I should have done n minus 1/2, but oh well, doesn't matter. b1 sine of 3 pi x over 2 plus b2 sine of 5 pi x over 2 plus etc. That has to be equal to 5 sine of pi x over 2, and if you prefer, plus 0 sine of 3 pi x over 2 plus 0, etc. Okay, so what is that saying? Well, that means that the coefficient of the sine of pi x over 2 terms have to be the same. So b naught has to be equal to 5. It means that the coefficient of the sine of the n equals, this is the n equals 0 term, this is n equals 1 term. These b1 better be equal to 0, b2 better be equal to 0, and so forth. So all of the bn's are equal to 0, except the n equals 0 term. So in other words, bn equals 0 for n bigger than 0, and b0 equals 5. So our final solution is u of xt. It just contains one term. We don't need an infinite sum. We shouldn't put an infinite sum there. It's one term. So here's our, let me box our general solution. It's just the n equals 0 term. So we get, which is 5 times sine of pi x over 2 times e. Now we need this thing when n is 0. So e to the negative, what is that, c pi over 2 squared t. And that is the particular solution that satisfies this initial condition. Notice that if we take the limit of this as t goes to infinity, it goes to 0, and that's exactly what we expect using our physical intuition. Finally, we come to our last example, which involves a type of boundary condition that we have not yet seen, though perhaps by now we should have. Obviously, I've run out of clever ways to number these. This is a boundary and initial value problem for the heat equation. It's the same PDE, except now instead of specifying the temperature or the rate of change at the boundary, all we're saying is that the temperature has to be the same at the left endpoint and the right endpoint. So here's a picture of that. So this is x equals 0 and this is x equals 2 pi. The initial condition is this trig function, 2 plus cosine of x minus 3 sine of 2x. I don't know how I'm going to be able to draw that well, but it looks a little bit like this. I'll do my best. And the only requirement is that the temperature has to be the same at both endpoints. So a better model than just a bar of length 2 pi that has this arbitrary condition is that this is not really a straight line, but it is a circular wire or circular bar, and x represents the angle in radians. So maybe this is x equals 0, and if this is theta, then this might be x equals theta. So obviously the temperature at any angle theta better be the same as the temperature at that theta plus 2 pi. Although actually we're only specifying 0 and 2 pi. But we will see that we'll have to have this periodicity for u as well. Let me try to, I don't know if I can do this, sketch this graph on top of, I'm really not going to be able to do this well, but I can sort of fake it. So this is what maybe the temperature is initially. How does that look? Okay, so first of all, what's going to happen as t goes to infinity? Before we do any math, let's just try to understand. So this is going to flatten out. I'm going to use a different color just so it doesn't get too confusing. So it'll flatten out like this, and then eventually it will approach, not surprisingly, the average temperature. Because the heat is trapped on the bar. That's what happens with these boundary conditions. There is no boundary. Okay, let's solve this. So as before, we're going to assume that there is a solution of the form f of x g of t. Let's take derivatives and plug it back in. So ut equals f of x g prime of t, and uxx equals f double prime of x g of t. Now, we don't have zero boundary conditions here. We have these things, and let's see what those entail. So u of 0 t, that is f of 0 g of t, and that has to be equal to u of 2 pi t. So u of 2 pi and t equals f of 2 pi g of t. So these have to be equal. So a number times g of t equals a different number times g of t. That means these numbers must be the same, because g of t is a non-zero function of t. So we get right away that f of 0 equals f of 2 pi. That's all we know. F is 2 pi periodic. It could be sines or cosines. Okay, let's plug these back into the PDE. So plug back in, and ut is f times g prime equals c squared times uxx, which is f double prime g. So as before, we're always going to divide by c squared fg, c squared fg. And as before, the f's cancel on one side, and the g's and the c's cancel on the other side, and we get g double prime divided by c squared g equals f double prime over f. And since the left-hand side depends only on time, not on position, and the right-hand side does not depend on time, then it must be equal to a constant. Let's call that negative lambda. Okay, so this gives us two ODEs. We have f double prime equals negative lambda f, and g prime equals negative c squared lambda g. And we have these two boundary conditions for f. So we have f of 0 equals f of 2 pi. So what does that tell us? Now, we really should do 3 cases before. So I'm not going to do them all, but I will say that case 1 is lambda equals 0. We get f double prime equals 0. That means that f of x equals ax plus b. And yes, so this is a straight line that has to take the same value at 0 and 2 pi, so it has to be a horizontal line. So we get that f of x is a constant. Let's call it a naught over 2 instead of just b. So, okay? Case 2. I really could have done this in the lecture on boundary value problems, but I'm doing it now. So lambda is negative omega squared. So now we have f double prime equals omega squared f. So this is cinches and coches, and cinches and coches are not periodic, and so I'll just say f of x equals a cosh of omega x plus b sinh of omega x, and then I'm going to say dot 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 f of x equals 0 with these periodic boundary conditions. That's a good exercise. I'm not going to do it. So finally, the last case is case 3. Lambda equals omega squared. So we have f double prime equals negative lambda omega squared f. And we get that f of x equals a cosine of omega x plus b sine of omega x. Okay, now what? So using those boundary conditions, well, remember that this is a single sine and cosine wave. That's shifted with a different amplitude if you want. And the only thing that we know is that f of 0 equals f of 2 pi. So cosines or sines will work as long as the frequency is correct. So this thing here has period t, which is 2 pi over omega, right? And this condition here, these boundary conditions, tell us that the period of f better be, well, it could be 2 pi, but it could be 2 pi over n. So 2 pi over omega equals 2 pi over n. That tells us that omega equals n. So that's what we get for omega. So in other words, we get that lambda equals omega squared, which is n squared. So omega equals n, and lambda equals n squared. So those are our eigenvalues. So now we have for each n, 0, 1, 2, etc., we have fn of x is, I'm going to call it an cosine of nx plus bn sine of nx, and we get that gn of x. So this is now equal to negative c squared n squared g. So gn of x is e to the negative c squared n squared t. And I'm leaving the a and the b both in here and not putting a c here. And that doesn't matter. They're going to get absorbed. So finally, we have so u of x and t is the infinite sum from n equals 0 to infinity of, what do I want to call it? How about an cosine of nx plus bn sine of nx times e to the minus c squared n squared t. And if you want, actually, how about instead of n equals 0, why don't I start at n equals 1 and I add a naught over 2 in there? Because it doesn't matter what we call that constant term. So this is our general solution right here. Now let's find the particular solution that satisfies the initial condition. So this is going to be just like what we did before. We are going to plug in t equals 0. So if we do that, we get that u of x 0. So now we have a naught over 2 plus n equals 1 to infinity of an cosine of nx plus bn sine of nx. We have to set that equal to the initial condition, which is 2 plus cosine of x minus 3 sine of 2x. So if this Fourier series with infinitely many terms equals this Fourier series with only 3 non-zero terms, then that tells us that this 2 better be a naught over 2. This 3, oh, I missed one. This 1 better be a1, the cosine of one term, and this negative 3 is the b2 term. So this is b2. So our final solution, u of xt, is this thing here, except we only have 3 terms. We have the constant term, which is 2, so that's 2. And then we have the a1 term, so that's equal to 1, so plus 1 times cosine of x times e to the negative c squared 1t. So e to the negative c squared t. And then we have a assigned term, so the n equals 2 term. So this is minus 3 times sine of 2x, put a dot here so you can tell, times e to the negative c squared 2 squared t, so negative 4c squared t. And this is our final solution, our particular solution that satisfies the periodic boundary conditions.